we're going to talk about histograms. Now, in your book, they go into how you do a frequency distribution in Excel. If you want to do it that way, that's just fine. We are going to be using StatCrunch, and we'll look at how to do a histogram with StatCrunch, and it'll do the frequency table for you. So we will look at that. The first kind of graph is a graph that is extremely important in statistics, and it might be one you haven't heard about before. And that's called a histogram. It's like a bar graph, but the bars touch because we are going to use interval data. Remember last time we talked about the types of data? Well, we're going to have continuous data. So, we use a histogram when we have continuous data, where that data that's represented by that bar could be anywhere in there from the lower limit to the upper limit. We put the classes on the horizontal scale, and we do the frequencies on the vertical scale. So here are our pulse rates, and you see this graph that we've already looked at. And on our histogram, we use I want to get the words right, we don't use the lower class limit when we draw our histogram, but rather we use the class boundaries. So the number that we see here are the class boundaries. So now sometimes they have the class boundaries, sometimes they use the class midpoints, and sometimes we use the lower class limit. This does introduce a small error, but in my opinion, this is an easier histogram to understand. So along the horizontal axis, we use the class boundaries or limits, and on the vertical scale we use the frequencies, either absolute frequency in number or relative frequency either as a decimal or a percent. So here we have relative frequency, so you can see that. Now, we do a histogram not to do a histogram, but so that we understand the data. We want to see what it looks like. We want to see that shape, that center, and the spread. And when we do that, we might come up with a bell-shaped curve. And there's a whole lot of stuff we can do if it is a bell-shaped curve. And we'll add those things as we go through the course. So here is some data, and you can see that if we would smooth out this curve, that it starts small and it grows big and then it gets small again. And so this is roughly a bell-shaped curve. So we can say that this distribution is symmetric. It's bell-shaped. That means that it has it's unimodal, has one peak. We can see how spread out the data is, so we can see the spread. And we can estimate the variation. We'll talk about how to do it by eye, but because technology is so available to us, we won't need to guess what that is, and we won't need to do that by eye. On the next slide, I'm going to introduce a data set that I've used for quite some time. You can kind of see from the age of the data. So this was an introductory statistics class in the spring of 1997 at VCU, and as we go through, here is the weight data. So on the first day of class, all the students were weighed, and this is simply the raw data. So then what we did was we're going to make a frequency table. Alright, so let's make the frequency table, and let's look at how we're going to do it. Well, there are 53 individuals. Take the square root of that at 7.2. Let's make it 8. Our range is 100 at the lowest, 260 at the highest, and divide that by 8, so we get a class width of 20. And so notice this is that less than notation I was telling you about, and we have our count. And this is count. It's not relative frequency, it's not cumulative frequency, it's straight frequency. And here we have our histogram. Now, this says that the left endpoint is included in the group, the right endpoint isn't. So in other words, this goes from 101 to, this goes from 100 to not quite 120. This one goes from 120 to not quite 140. This one goes 140 to not quite 160. Now I am going to pause here and let's go out to StatCrunch and look at that. Okay, so let's look at how we do a histogram in StatCrunch. I'm in my MathLab course. I'm going to click on StatCrunch. Because this is a data set that I entered, I'm going to go to the StatCrunch website, and when you're logged into your my MathLab, you're automatically signed in to StatCrunch. If you go to StatCrunch and you don't have my MathLab open, you will log in with the same username and password that you used on my MathLab. I want to go to a data set that I entered, so I'm going to do my data, and there is my chapter 2 weight data. So there are my individuals. I want to go to the graph, and I want to do a histogram. I want to look at the weight in the columns, and it's a frequency. You could do relative frequency density. I'd recommend just keeping it frequency. And we already decided that our class widths will be 20. Now, one thing we need to do when we do a graph is all good graphs have titles. Let's go ahead and do our x-axis label. That's going to be weight. And the title of our graph will be student weights in okay, whoops, better spell it right. I want spring. They're not going to give me spring. Well, I'm not sure what happened there. I don't have a graph. So let's do it again. Weight, width is 20. Our x-axis is going to be weight. Our title will be let's compute. And here is my histogram, and it looks very similar to the one that's in the textbook. Okay, so we're here back at the PowerPoint, and you can see how this histogram looks just like the histogram. Well, it looks very similar to the histogram we just built in StatCrunch. Let's talk about skewedness. And what happens is, if our data is not symmetric, if it's squished to one side or the other, it's skewed. And remember, when it's skewed to the right, we also call it positively skewed. That means that the tail points to the right. When it's left skewed, it's negatively skewed and the tail points to the left. Let's look at this data set, and let's look at the green one. And the green one is relatively symmetrical. It's bell-shaped. As we look at the red one, it's relatively uniform. We could best describe this as a rectangle. So it is symmetrical, but it's a uniform distribution, where we would expect values in our classes to happen at the same frequency throughout. So this might be, if I have 10 marbles in a bag, each one with a digit on it, and I draw them out and replace them, how often is it going to happen? Well, right there, they're going to happen about the same amount of time. As we look at this white distribution, notice how it extends, how the right tail is longer. So this is right skewed. In the brown one, we have the left tail that's longer. So this one is left skewed. Now, as we are going through the data, sometimes we want to look at normality. And when we look at normality, we do a normal quintile plot. And I'll be really honest with you, our normal quintile plot is something you do with technology, and you want to get the points are reasonably close to a straight line. So let's look at the next slide. So here we go. Okay, pretty close to a straight line on this top one. So that's probably relatively normal. Notice that on the lower one on the left, notice that our data points have a pattern, and it certainly is not a straight line. So this would not be a normal distribution. Then, if we look at the lower left one, well, they're close to a straight line, but you can see a definite pattern where in the lower part, most are above the straight line, and in the upper part, most are below the straight line. So this is not normal. It does show that there's a symmetric pattern, but not a straight line pattern. And we'll talk more about what this means later as we go through. Okay, let's talk about graphs. Now, graphs are useful things, but I'm going to tell you that graphs can mislead us because as human beings, our senses are fickle things. And I will tell you that there are a lot of people who like to put things in graphs who don't know what they're doing. And while they make their graphs very attractive, they're just wrong. The other thing is, we have people who make graphs that are very well aware of what they're doing, and they want to trick you into thinking what they want you to think rather than what is true. So, graphs reveal important characteristics of the data, and on the right side here we've got a list of possible kinds of graphs. Now, a frequency polygon is simply, it's very related to a histogram, but rather than bars, we just have points at the class midpoints, and then we just connect the dots. And when you do a relative frequency polygon, it does make it easy to compare two sets of data. So we have the men that was on one of the previous slides compared to the women who we've been working with. Now, an ogive or ogive is a cumulative frequency. So ogives always end up at your total number of individuals in your data set. And so from an ogive you can just read how many are less than that very quickly. Then you have a dot plot, and a dot plot is a little bit like a histogram. And again, here are the pulse rates that we've been dealing with. And what they do is each dot represents the same number of individuals. So in this case, I don't know if it's one or not. I haven't counted the dots. But sometimes you'll have, you know, thousands of people or thousands of individuals represented in a dot plot, and you don't have thousands of dots. And then we have stem and leaf plots. Now, the stem and leaf plot is another way to quickly make a histogram. And we could do it for quantitative variables, and we separate each observation into a stem and a leaf. And you'll get the idea here in just a moment. So we're going to write the stem in the vertical column, and then the leaf is the remaining part of the number. Let me show you what I mean. So here is our weight data that we've been dealing with, and we're simply going to draw a line between the tens and the ones. So now what happens is the tens is our stem and the ones are our leaf. So we'll put our stems in order, and then we will add the leaves. So let me show you what we're going to do. And let's look at our data, and we go from 100s up to, I thought we had somebody that was 260, but I don't see him. He's there somewhere. Oh, there he is. Okay. So in other words, we have people who are might be female gymnasts, and then we have a lineman for the football team. And we have everybody in between. So here we have our stems, and then we're going to look at our data, and we're going to fill in our leaves. So let's just look at a person who, our first person is 192. So we're going to find the 1 and the 9, and we're going to put the 2 right there. Then we're going to look at our next person, that's 152. And so the 1 and the 5 go there, and then we're going to put the 2 right there. And then our third one in our data is 135. So we're going to find our stem of 1,3, and then we're going to put a 5 in the next column. I like to do this on graph paper. Now you can't see it from our slide here, but if you put one number in a square, then it really does come out to be a nice approximation of a histogram. The other thing you can do is take your lined paper and turn it, and then you have your lines act as the columns in your graph paper, and then if you put one number in a column, then again each number takes up the same number of space and makes a really nice quick approximation to a histogram. And this is what we would get if we finished out data for our weight data, and you can see that it looks similar to our histogram, but now our classes aren't 20 pounds wide, they're 10 pounds wide. So it's going to look just a little different. Now, sometimes when we have very few stems, or we have a very small set of data, what we do is we split the stems. And so what we do is we use the lower half of the 150s, 0 through 4 goes in the upper 15 stem, and then the 5 through 9 goes in the lower. And so it's going to look a little bit different. Oops, that isn't what I wanted to do. It's going to look a little bit different. So now what I'd like to do is let's stop and let's look to see how we do a stem and leaf plot in StatCrunch. So hold on just a second here. Okay, so let's go back to our data set and let's do a stem and leaf plot. I'm just going to slide our histogram off to the side. I'm going to go back to graph and stem and leaf, and I'm going to do the weight, and I don't want it to trim anything, and I want my leaves in ones. I want the ones to be my leaf, so the hundreds and the tens are in my stem. And there we go. We have our stem and leaf plot. Looks very much like the one that we looked at in the slides. So pretty easy, huh? Okay, so again, this stem and leaf plot looks very much like the stem and leaf plot we built using StatCrunch. Okay, now we use bar graphs when we have categorical data usually, or we have qualitative data that is not continuous, that would be discrete. Remember, like the number of eggs a hen lays, or etc. And there, when we do a bar graph, there are spaces between the bars. That's the difference between a bar graph and a histogram. Now, so here we have decades, and so the decades are separate, and that's why they do not touch. This happens to be a side-by-side bar graph, where not only are we comparing incomes in the decades, but we're also looking at male-female incomes during the decades. And you can see how we would represent that. Now, when we put the bars in descending order according to frequencies, then it's a Pareto chart. And I would rather see this Pareto chart with spaces between the lines, because you can see in this first category it's networking, and in the second category it's newspaper ad, and in the third category it's internet. They do not flow into one another. That's usually why we put spaces between the bars in a bar chart, to show that our categories are very, very separate from each other. Then we have a pie chart, and a pie chart is very good for showing what proportion is represented, a part of the whole. It's very easy to see how it compares. So if we're looking at how people got a job, you can see that networking is the biggest part here, where a newspaper ad is next biggest, applied in person, the internet through an employment agency, the smallest part is through a school. So it's nice to get an idea relative to the whole. And then we have a scatter plot, where we plot things on the x-axis versus the y-axis. And so here we are looking at cricket chirps as they vary by temperature, and you can see that when the temperature is low, the number of chirps is lower. When the temperature is higher, the number of chirps is higher. And then we have a time series graph, which is kind of like a scatter plot, but on our x-axis is always time, and our y-axis is what we're looking at. And you can see this is the Dow Jones Industrial Average high, and you can see as this was going that in the year 2005 the Dow Jones was above 12,000. If you watch the news lately, it's right around 17,000. So a lot has happened in the last 9 years. But it shows how that has changed over time. When you have a small data set, a table's better. You want to be, you don't need your graph to be cute. It should be very clear and concise. And you don't want it to distort the data. And we'll look at some good graphs and bad graphs here in the next slides. Your ink should be in the graph and not in the design features. So you don't need to be cute when you're doing a graph. Again, don't use cross-hatching. Don't use areas or volumes from one-dimensional data. Here's an example of that. Looking at the value of money. In 1980 dollars, a dollar was worth a dollar. In comparativeness, in 1990, that same dollar was only worth 63 cents, and in 2005, that same dollar was only worth 42 cents. So 42 cents in 2005, a dollar bought 42 cents worth of 1980 product. Okay, now these are very nice graphics, and they're very neat and they're very clean. But what we are looking at is we're looking at one-dimensional data. And if you took a ruler and you measured your length of the dollar in the hand, the 1991 would be 63% of the length of the 1980, and the 2005 would be 42% of the 1980. But not only has the width changed, but the height has changed too. So what happens is the area of our 2005 dollar is less than 42% of the 1980 dollar, because we shrunk it in 2 dimensions. So we need to be careful. This is a bad data set. This is a bad graph because we're using 2-dimensional figures for 1-dimensional data. Now, this is the kind of chart that you find in Consumer Reports, and Dr. Tuft identifies this as being a good graphic, easy to read and easy to understand. Because there's a lot more green over here under the Firebrand, I'm going to say chances are that it's a better car than the Speedster. There's a lot more red over here. It's real easy to tell that. Good graphs describe the data. Again, distribution, center, spread, outliers. Remember, shape, center, spread. Those are our magic words. They help us explore the data to reveal the characteristics. And they help us to compare the data by side individual visual representations. And the visual thing is what's part. But not all graphs are good graphs. Some graphs contain errors. Some are technically correct but misleading. So you need to become a savvy consumer of graphical statistics. For instance, looking at these two graphs, it's like, oh my gosh, the graph on the left, look at the difference between Democrats, Republicans, and Independents. But notice in the graph on the left, we did not start at 0. The graph on the right, we actually started at 0. So when you see the whole picture, there's not that much difference in opinion as we see when we cut it off. And so be cautious when you see that on a graph. Pictographs are very easy to have distortion because we're looking at one-dimensional data using two-dimensional figures. Again, we're using the dollar. It's very busy. We're using the length and width. These are not proportionally incorrect, but using that dollar, it's just difficult to understand. Again, you want your ink in the graphics, not in the pretties. And here we have the same data and we use boxes. Oh my gosh. Not only are we changing the width, we're changing the height and the depth. And so even though the last box shows an income 4 times of the smallest box, this comes out to be 4 times 4 times 4. Our eye sees a 64 time increase from the first box to the last box. So be careful. Don't do 3-dimensional figures to represent one-dimensional data. Now, here is a better representation of the same data, a simple bar graph. Notice that the width of each bar is the same, and it makes it a lot easier for our human brains to actually see the true difference. Notice it's a good graph because it has a title. We have uniformly distributed scales on the y-axis. Our x-axis is labeled. We start at 0. Now sometimes because of simply because of space, you can't start at 0. If that's the case, then what you do is, I call them lightning bolts. You put something in your axis to show that you have abbreviated it. Now, I use lightning bolts. It's to show that like you would have folded the paper. So let's go back because the lightning bolts aren't appropriate in that one, but it would have been in this graph. We should put lightning bolts here. Oops. We should put lightning bolts here to show that it doesn't start at 0. Okay, now again, I'm going to go through the active learning questions. You have these on your, you can print them out, you can look at them. If you need to pause between them, that's fine. I'll wait about maybe 5 seconds on each slide. Oops, I didn't want to do that, sorry.